Stephen Chu of Stanford, Claude Cohen-Tanuji of École Normale Supérieure France, and William Phillips of National Bureau of Standards USA have been awarded 1997 Nobel Prize in Physics for their pioneering experiments and theoretical investigations of laser cooling. These three professors have developed a method of laser cooling wherein the atoms can be made to cool to the temperatures of micro degrees Kelvin. The atoms are then floating in the traps, and the method developed by Chu, Cohen-Tanuji as well as Phillips makes us understand better the interaction of radiation with matter and many quantum phenomena that are associated with it. The method may find an application in atomic clocks or in microelectronics as well as in atomic lasers. The method developed by Chu, Cohen-Tanuji and Phillips have been used by Professor Eric Cornell of University of Colorado and have successfully experimentally demonstrated the Bose-Einstein condensation of ideal Bose gas. Since he has used this method, here is a professor who will explain to our viewers right from his own experimental methods the same laser cooling for our viewers. Pune University Physics Department is organizing an international workshop on condensed matter theory, and this 20th workshop, CMT 20, there has been many distinguished visitors. One of them is Professor Eric Cornell. Professor Eric Cornell is a professor of physics at University of Colorado and has a joint appointment as a staff scientist in National Institute of Standards and Technology. He got his PhD from Massachusetts Institute of Technology in 1990, and within 6 years has become a full professor of physics at University of Colorado Boulder. He did his PhD at MIT with David Pichard, and he is the person that led leading the team that had made the first experiment of experimental demonstration of a Bose-Einstein condensation of an ideal gas. So, hello Eric, I understand that the lasers are used for cooling purposes and say maybe something like micro degree Kelvin. Is it true?
It is indeed true, and a lot of people find it very strange when they think of lasers. They think, what could be hotter than lasers? After all, lasers are somehow, in many people's minds, the very definition of something that's hot. But in fact, you can use lasers, shine them into a gas of atoms, okay, and get to extremely low temperatures, perhaps within 1/1,000,000th of a degree of absolute zero, or 1 microkelvin, as you say.
Oh, I see. I mean, how does indeed a laser beam interact with the atom?
The laser beam shines, essentially bounces off of the atom. The photons come in, the laser beam is composed of photons. The atom absorbs these photons and scatters them back out again, and it feels a push from this, as a momentum from the laser beam, which the atoms feel as a force.
Well, won't it essentially increase the density of the gas so that temperature would normally be expected to rise of the gas rather than cool?
Sure. As I was saying before, in fact, it seems very sensible to imagine that if you shine a laser beam into a gas, the gas will get hot. Certainly, if you shine a laser beam on your hand, your hand will feel hot. The trick somehow is to use these forces to slow the atoms down. So, for instance, perhaps we have a laser beam coming in from the right and a laser beam coming in from the left, and in the middle we have a collection of atoms going in many different directions. The idea then is somehow to use the forces from the light to oppose the direction of the atom's motion and make them move slower. And remember, in a gas of atoms, moving more slowly is of course the same as being cold.
That's right, but how do you select such atoms? Because the atoms in a gas are randomly moving all around, and
the trick has to do with the Doppler shift. The Doppler shift is something we're all familiar with, usually in the form of sound. Just today I was walking on the streets of Pune, and a motor scooter came by. It was, as it approached me, it sounded its horn. Coming towards me, it was high. Beep. It went past me. Ee. It went lower. This is the Doppler shift. The Doppler shift we're most familiar with in the form of sound, but it also applies to light. For instance, if I am moving towards a light, that light will appear to me slightly bluer. If I'm moving away from a light, that light appears to be slightly redder. This is most commonly known in what's known as the red shift. When we look out at the distant stars, which are moving away from us, those stars appear to us to be slightly redder. The effect in light is a very, very small effect, but it can be useful.
But then, see, what you are talking about is essentially the things are as if moving in only one direction. So essentially what you are saying is happening in one dimension, whereas actually the gas has all kinds of directions of motion and many, many degrees of freedom. So how do you achieve this?
Well, actually we have the laser beams coming in from all directions. We have laser beams coming in north, south, east, west, up and down. And imagine that I am an atom, and I am moving, say, towards you. And from over your shoulder, there's a laser beam coming at me. The trick is we take the laser beam and we make that laser beam a little bit too red, which means to say the frequency is a little bit too low. So there's a laser beam coming over your shoulder at me, and there's a laser beam coming from behind me at my back, but I'm moving in this direction. Because I'm moving in this direction, the laser beam, which I see coming this way, appears a little bluer, a slightly higher frequency, and it becomes closer to the resonance frequency, the frequency at which I as an atom, most want to see the light. So I react from that light. That light pushes against me. On the other hand, the light which is coming from over my shoulder, this light, is because I am moving away from it, it becomes even more red. It is moved further away from resonance. I interact less strongly with that beam. So if I'm going towards you, I feel a push which opposes my motion. If I'm going to the left now, the laser beam going this way opposes my motion. The laser beam which is coming in from the right, I feel relatively small. If I have a collection of a great many atoms now, millions of atoms, each atom is going in a different direction, but each atom is able to select the laser beam which is opposing its direction of motion, and it slows it down. So we're able to slow the atoms down enormously to a much lower velocity, which of course means colder.
Well, so does it mean that atoms essentially come to a complete halt?
No.
Is this really an absolute zero?
Not an absolute zero. If they came to a complete stop, that would be absolute zero. They don't come to a complete stop similarly to the way, if you look at little smoke particles. You're familiar perhaps with Brownian motion.
Yeah.
The classic example is smoke particles. You look into a microscope at little particles of smoke in the air, and they're jittering around. They're wiggling around. They're not completely still. Even though somehow the smoke particles find the air viscous, damping. If the smoke particle were moving fast, it would quickly come to a stop from the viscous flow of air around it. But it never comes to a complete stop. The reason is that the air comes in discrete particles. Little atoms are continually hitting it this way and that way, so it never can come to a complete stop. Similarly with the atoms now being slowed down by the laser beams after all come in individual particles of photons, and the individual kicks from the photons hitting the atoms cause it to jiggle around, and that residual motion, which is not quite stationary, amounts to about 1 centimeter per second, 2 centimeters per second. In the atoms we work with, this corresponds to about a microkelvin.
I see. So what kind of an apparatus you have? Could you give some idea as to how you have achieved this?
Yeah, we can see a picture of my apparatus, and it shows a glass cell. The glass cell is perhaps 1 or 2 inches on a side. Inside is a very good vacuum, except for a small amount of this gas. And then coming in from all 6 directions through the walls of the glass are the laser beams, pushing the atoms together and slowing them down at the same time. So you can see in the center where these laser beams all intersect, there's a glowing ball of atoms. And this is the atoms which are being cooled by the laser beams.
Oh, I see. So, but how much is the vacuum conditions for this kind of equipment, how much vacuum is there, and what kind of atoms you are putting in the apparatus?
The vacuum is should be very good. After all, the vacuum serves to insulate the very cold atoms, which are within 1 or 2 microkelvin of absolute zero, from the glass. The glass, after all, is at room temperature, 300 Kelvin. So the vacuum has to be much better than inside a conventional vacuum flask, perhaps 10 to the minus 10 torr. We typically use atoms such as, we prefer the alkali atoms because it's easy to get laser beams whose color matches the alkali atoms. In our experiments, we most often use rubidium, but sodium, lithium, potassium,
is it because
they all work well.
Easy to evaporate, and you get a fair amount of
yes.
beam?
It's also very easy to evaporate. Even at room temperature, the sublimation vapor pressure of the alkali metals is good enough for us to collect some vapor and cool it down. But most particularly because the wavelength is convenient for inexpensive lasers.
I see. Now, really the question is, suppose you have made all these atoms almost stand still, okay? Then the question is, what kind of experiments can you do with it?
A lot of different experiments you can do with these very cold atoms. From my personal perspective, I work for the Institute of Standards and Technology. We're interested in measuring things very precisely. The slower something moves, the more carefully you can measure it. For instance, atomic clocks, as you know, are based on cesium atoms, currently in thermal beams traveling at many hundreds of Kelvin of energy. If you could slow those atoms down to a very slow temperature and move them very slowly through your resonance machine, you could make a much better measurement of the resonant frequencies inside the cesium atom, which is what defines our standard of time. So the international standard of time is based on resonance measurements in cesium atoms, and we could make a better clock if we had colder atoms. This is a more applied thing. There are also more theoretical or more purely scientific interests, such as correlations in velocity distributions, and my particular interest, of course, is in Bose-Einstein condensation.
Oh, I see. So, thank you very much, Eric. It was a great pleasure talking to you with your excellent experiments, and I hope you will be able to achieve what you want.
Well, thank you very much for giving me an opportunity to explain it to you.
Okay. Pune University Physics Department is organizing an international workshop on condensed matter theory, and this 20th workshop, CMT 20, there has been many distinguished visitors. One of them is Professor Eric Cornell. Professor Eric Cornell is a professor of physics at University of Colorado and has a joint appointment as a staff scientist in National Institute of Standards and Technology. He got his PhD from Massachusetts Institute of Technology in 1990, and within 6 years has become a full professor of physics at University of Colorado Boulder. He did his PhD at MIT with David Pritchard, and he is the person that led leading the team that had made the first experiment of experimental demonstration of a Bose-Einstein condensation of an ideal gas. Hello Eric, welcome to the University of Pune.
Thank you very
It's
much.
Very interesting that you have performed very fundamental experiments on Bose-Einstein condensation, and millions of viewers from this country would like to listen to your experiments. I just want to ask you, what is the contribution of Satyendranath Bose to quantum mechanics?
What Professor Bose did is introduce the concept of the indistinguishability of particles. His particular application was to photons, and thus began what we now call the field of quantum statistical mechanics.
I see. How did Einstein extend some of his ideas?
Einstein took Bose's idea, which was originally for photons, and extended it to particles in general, and in so doing, on a purely mathematical basis, Einstein discovered that if you get particles, indistinguishable particles such as bosons, sufficiently cold and dense, you get a phase transition at very low temperature in which many particles all pile up in the lowest available energy state of the system.
I see. Essentially, for finite number of particles, he did his extension rather than infinite number of particles.
Sure.
I see. Who christened the name Bose-Einstein condensation?
That term was coined by Fritz London. In the 1930s, people were doing experiments with liquid helium, and they discovered that if you get liquid helium cold enough, the viscosity of the fluid can vanish. And this was people found this truly miraculous, and indeed people still find it miraculous. It's one of the amazing results of physics. And Fritz London suggested that Bose-Einstein condensation could be responsible that for this phenomenon, that in fact you could have a very vast number of the helium atoms all participating in the same quantum mechanical wave function, and in this way flowing without viscosity.
Who are the colleagues in your experiment, and what is the importance precisely of your experiment? Because already there is a helium and
Sure.
people have observed superfluidity, but in spite of that, what is the importance of your experiment?
Well, the work I'm going to tell you about today was done in close collaboration with my friend and colleague, Professor Carl Wyman from the University of Colorado. And what we did is develop Bose-Einstein condensation in what we call a dilute system. Helium is a very strongly interacting system. It's a liquid, after all, and not a gas. And the original concept, as conceived by Bose and Einstein, was an ideal gas, a non-interacting system, a very pure system in which, even though the interactions between the particles were very small, you could still get a phase transition, a purely quantum mechanical phase transition. And it was this idea that we wanted to try and realize now in a gas, a very thin gas, instead of in a liquid.
I see. So you used alkali atoms for that, especially
Yes.
rubidium, is it?
Yes.
I see. What was the reason why you are using rubidium? Because one would normally think that rubidium has one valence electron and electrons are fermions rather than bosons. So how can a rubidium atom condense?
Well, to get Bose condensation, of course, you need particles which are bosons, particles which have an integer spin, 0, 1, 2, like this. And it's true that all the alkali atoms have an extra unpaired electron. But of course, the alkali atoms are neutral, which means if they have an extra electron, they must also have an extra proton. And in sum, the total number of fermionic particles that make up an alkali atom is even. So the total spin must be 0, 1, 2, 3. And in this way, we make what's called a composite boson, and the overall behavior is that of a symmetric particle.
I see. How do you get atoms really so cold?
To get atoms that cold, and although we haven't mentioned it, Bose condensation occurs at an inconceivably low temperature, below 1 microkelvin. To get them this cold requires two techniques, which we use in sequence, a hybrid technique. The first technique is laser cooling. Actually, we have the laser beams coming in from all directions. We have laser beams coming in north, south, east, west, up, and down. And imagine that I am an atom, and I am moving, say, towards you. And from over your shoulder, there's a laser beam coming at me. The trick is we take the laser beam and we make that laser beam a little bit too red, which means to say the frequency is a little bit too low. So there is a laser beam coming over your shoulder at me, and there is a laser beam coming from behind me at my back, but I'm moving in this direction. Because I'm moving in this direction, the laser beam, which I see coming this way, appears a little bluer, a slightly higher frequency, and it becomes closer to the resonance frequency, the frequency at which I, as an atom, most want to see the light. So I react from that light. That light pushes against me. On the other hand, the light which is coming from over my shoulder, this light, is because I am moving away from it, it becomes even more red. It is moved further away from resonance. I interact less strongly with that beam. So if I'm going towards you, I feel a push which opposes my motion. If I'm going to the left now, the laser beam going this way opposes my motion. The laser beam which is coming in from the right, I feel relatively small. If I have a collection of a great many atoms now, millions of atoms, each atom is going in a different direction, but each atom is able to select the laser beam which is opposing its direction of motion, and it slows it down. So we're able to slow the atoms down enormously to a much lower velocity, which of course means colder. And the second technique, which we do second, is evaporation. We cool the atoms with the lasers, we turn the lasers off, and then we turn on a very strong magnetic field which acts very much like a bowl, an intangible bowl, which holds the atoms, insulates them from the walls of the chamber, and provides a mechanism for cooling known as evaporation. Just as if you have a cup of tea, the steam coming off is the most energetic of the tea molecules, breaking free from the tea work function and taking away extra energy. Well, also, if you have a magnetic bowl, only the most energetic atoms can roll up and over the lip of the bowl, and they take away more than their fair share of energy. The remaining atoms cool down.
I see. So, but suppose you have all this gas, cold gas. How do you measure such low temperatures? How low are the temperatures and how do you measure them? Because no thermometer can conceivably withstand or can measure really those low temperatures.
It's an excellent question. If you were to, any thermometer would be much hotter, and if you were to touch the gas with a thermometer, the gas would immediately boil away. So we measure it by measuring the velocity distribution. And we can see this in the picture. We're holding the atoms in the bowl. We suddenly open up the bowl by turning off the magnetic fields, and the atoms fly apart in every direction. After they've been allowed to fly apart ballistically for a few minutes, for a fraction of a second, bang, we snap a picture of them, and we see the spatial distribution of the atoms. If the atoms are going fast, the spatial distribution is large. If they're going slow, the spatial distribution is small. You can see these pictures behind us of that same distribution.
I see. Now, how do you see that the Bose-Einstein condensation has indeed occurred?
What we look for is the characteristic two-component distribution. Just as in superfluid liquid helium, you have the normal component of helium and the superfluid helium. In the alkali gas, when we get them cold enough, a very large percentage of the atoms pour down into the lowest available energy state of the system, which is barely moving at all. And so when we take a picture, we see two components. We see a broad, round distribution of velocity, which is the ordinary atoms, and in the center we see a spire. You can see these distributions behind us now. You see a spire of very low velocity atoms which correspond, they're almost stationary, and these correspond to the Bose condensation.
And so is it a substantial or a macroscopic fraction?
Oh, it's a very large fraction. In fact, we can, if we get them cold enough, we can put nearly 100% of the atoms into the ground state, as we say.
Yeah, because this is certainly very much different from what helium has. The condensate component is really low.
The interactions in helium are so strong that, as you say, perhaps only 10% of the atoms ever really participate in this ground state.
Yeah, on the other hand, you see about 100% condensation.
Yeah, at least 90%.
I see. You have measured these things?
Yes, we've measured the relative fractions of the atoms which are in the central spire compared to the low atoms around them.
I see. Can you describe your apparatus? What is the role played by magnetic field? How is it creating a trap? And
the apparatus is a series of magnetic coils, as we can see in this photograph or in this sketch. Magnetic coils wrapped around a glass box. With the laser beams coming in. The laser beams come in, they cool the atoms. When we turn off the laser beams, we turn on the magnetic fields. These very powerful magnetic fields form the magnetic bowl. We do the evaporative cooling from the magnetic bowl, and then we turn off all the fields, and to take a final picture, we send an additional laser beam in from the side. That laser beam passes through the atoms absorb some of the light, and now there's a shadow in the middle of the laser beam, and that shadow falls on a TV screen, a TV camera, And that's that image which is processed to make these computer pictures behind us.
I see. So it is really a coordinate space picture.
It is indeed.
I see. Can you give me some details regarding the magnetic field? How strong are these fields, and what are the shapes?
In our particular trap, the fields are on the order of several hundred Gauss per centimeter, which is large but not incredibly large fields. And in addition, there's a time varying component which makes the trap more stable. We call it a time averaged orbiting potential trap, or TOP trap, which is a very tightly confining but stable trap for neutral atoms. It acts by attracting the little magnetic moment that each atom possesses and pulls it in towards the center where the field is lowest.
I see. Can you see what are the applications of this apparatus and the technology which you have developed regarding this in reference to this Bose-Einstein condensation experiment?
Well, I think it's too early to say. We must remember that when lasers were first discovered, they were just a novelty, an interesting scientific development. Now there are lasers in supermarket scanners and compact disc players and all around the world. I don't want to tell you that Bose condensation will ultimately be as useful, but certainly there are very close analogies between a laser beam, which is a beam of coherent photons all doing exactly the same thing, and a Bose condensate, which is, after all, is a collection of coherent atoms all doing exactly the same thing. In the future, perhaps it will lead to improved precise measurements or very precise monoenergetic atom beams which can be used in a lithographic format.
I see. So, thank you very much, Eric.
And thank you.
It is a pleasure talking to you.
I've enjoyed this myself.